All right, welcome to Accelerated Math. This is add and subtract complex numbers, but don't let that word complex fool you because you're going to find out it's not that bad. Even though we're dealing with this letter I, it's not a variable. It represents the square root of -1. It's an imaginary number. You can't calculate the square root of a negative number. So way back in 1777, I think, or something, somebody formalized this as we're going to use I for imaginary number for the square root of -1. Okay, so what are we going to do? How are we going to deal with I? Well, we actually, even though it's not a variable, we're going to treat it a lot like a variable. Okay, and we're going to simply combine like terms. This is an addition problem, so we're going to drop the parentheses and we're going to combine like terms. So I'm going to rewrite this by dropping the parentheses, 8 minus 2i plus 6 plus 9i, and then in combining like terms, I like to, hey, underline something that these two are alike, and maybe do something else for the other ones, just making sure I get the sign in front of it. Negative 2i and positive 9i, that's plus 7i. And that's my final answer. I can't combine those. They're not like terms. Some people may have written that as 7i plus 14, and that's true, but it's simply not in what we will call the standard form of a complex number. Okay, the standard form of a complex number is going to be in the format of a plus bi, where a, whoops, this is not it, sorry, a plus bi, where a is the real number or the real component of it, and bi is the imaginary component. Okay, so that's a standard form of a complex number. This one is not. Moving right along, we got the only thing different about this one is it's a subtraction problem. All right, and back when, if you ask a third grader or second grader, what is 7 minus 4, most of them will tell you it's 3. But if you turn it around and ask them what's 4 minus 7, they'll tell you, well, you can't take 7 away from 4, there's not enough. Okay, but we know working with negative numbers that what we're going to do is we're going to change this to addition. So subtracting a positive is the same thing as adding its inverse. Okay, so subtracting a positive is the same thing as adding its inverse in this case. So 4 minus 7 is the same thing as 4 plus -7, and that helps us out because now it's an addition problem, and we're going to invoke the addition rules that if the signs are different, we're going to take the sign of the larger absolute value number, so we're going to take the sign from that one, and we're going to subtract 7 minus 4, then subtract the absolute value. 7 minus 4 is 3, and that's how we come up with that. Okay? All right, so we're going to do something similar here in that we're going to change this to an addition problem, and then we can drop these parentheses. So we're going to change this to an addition problem, but subtracting this is going to be the same thing as adding its inverse. So we need to change the sign of each thing afterwards. And you don't do anything to the front. Some teachers teach that as keep, change, change. And they're saying keep this, and change all the signs in here. And that's a good way to remember it. So -4 minus 5i, now we've got an addition problem, plus -9 and positive 8i. Now we're back to it's an addition problem. We're going to combine our like terms. That's -13, and we're going to combine those like terms, the imaginary components, and that's plus 3i. And that's in the right format. If it was 3i minus 13, it would not be in the right format. We'd want to switch it around. All right. Last one, square root of -80. Now, if you go to a calculator and you try this, it will not work. So what we're going to do is we're going to factor out from this the square root of 80 and the square root of -1. That's true. 80 times -1 is -80, so we factored it. But this part over here we know as I. All right, so it is not under the radical. It is out by itself. Okay, then we're going to continue to factor 80. And, different ways of factoring this, but 4 and 2, I get it down to all prime numbers, 5 and 2. Once you get it down to all prime numbers, then you're looking for duplicates to kind of combine them back to get a square number. 2 and 2 is 4, the square root of 4 is 2. So any combinations get out as a single value, and the 5 had to stay in there because it had no duplicate value is not a perfect square. And so it couldn't be combined with anything else to make a perfect square, so we can't square root it. We leave it in there. The 2 and 2 on the outside get multiplied because they were divided to get them in the first place for root 5. Okay, some people would have said, well, grab a calculator, and certain scientific calculators will get that into that format. Other people may have said, oh, that's 16 and 5, and the square root of 16 is 4, and the 5 you can't do anything with. So either way, you come back to 4 root 5. Okay, but don't forget about our I out there. Okay, we can't just throw that out. So this is labeled 4I root 5. And then the 45, again, you get an I out because it had a negative in it. That's negative 1. And the 45 simplifies to 3 root 5. Okay, and this was an addition problem, 3I root 5. Yeah, 3I root 5. And we're adding these. These are now like terms or like radicals because the radicand, that part inside the square root, is the same. So I've got 4I of them and 3I of them. So together I would have 7I of them specifically being root 5. That's your answer. Have fun with it.